One more topic I would like to cover related to descriptive statistic is distribution. In this topic, I would like to talk about frequency distribution and histogram, normal distributions, and the z-scores and the probability. So let's take a look first at what is frequency distribution. So by definition, frequency distribution is a representation either in a tabular or graphical format that displays the number of observations within a given interval. It sounds kind of hard for you to understand now. So this is why I'm going to use an example to show you. First of all, what do we mean in a tabular format? And then later, I also will show you what I mean by a graphical format to show frequency distribution. Okay, let's take a look at the example I have here. I have 90 homes, and I have the energy consumption of these 90 homes. So if you look at these 90 numbers I have here, I kind of order them from the smallest to the largest. So the smallest will be 2.97, then the largest is 18.26. So what I'm going to do with these 90 numbers, I'm going to go to my next slide. So what I did is for these 90 numbers, I actually determined on 90 no I'm sorry on nine classes. So for example, the first class, I have energy consumption from 1 to 3, larger than 1, smaller than 3. Second class, energy consumption between 3 and 5, larger than 3 but smaller than 5, and so on. So I have 9 classes, or to use a more common word will be 9 categories. But I would say I use classes. I have 9 classes, and each class here has an interval. So the first class, I have an interval of 2, second one, interval 2, interval 2. So all these 9 classes, each one has an interval of 2. And then after I did that, I go back to my table, and then I say, let's count how many homes with energy consumption between 1 and 3. So I only have 1 home here. So I go back to my table. I call this table frequency table. I go back to my frequency table. I put 1 there. That means I only have 1 home with 1 energy consumption between 1 and 3. I will do the same for the second class, energy consumption between 3 and 5. So I go back to my table. I only have 1 home with energy consumption between 3 and 5. So I go back to my frequency table, and I put 1 there. For the third class, energy consumption between 5 and 7. If I go back to my table again, how many homes I have here with energy consumption between 5 and 7? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. I have 11 homes with energy consumption between 7 and 9. I'm sorry, 5 and 7. So I put 11 homes here. I will do the same and then go back and forth and then come to count how many homes I have in each interval or in each of these classes. So I put all those numbers here. So these numbers are frequencies. So if, for example, this number 25 means I have 25 homes with energy consumption between 9 and 11. So now I have already finished to put in all these frequencies. So let's go back to the definition. So frequency distribution is a representation in a tabular format. Display the number of observations within a given interval. Great. So you should be able to understand the number of observations within an interval. So within this interval, I have 1. Within this interval, I have 1. Within this interval, I have 11. So this is a tabular format for you to show the distribution, frequency distribution of the energy consumption of these 90 homes. Okay? Now let's take a look at relative frequency. So you will ask me, okay, how did you get this number? What I did is, because I have 1 home in this class, the total number of homes I have is 90. So I'm going to use 1 divided by 90. So I got 0.011. Say, you understand this means I can convert 0.011 to 1.1%. Because I use 1 divided by the total number 90, I got this. So this number means I have 1.1% of a home within this class. Or I have 1.1% of a home with energy consumption between 1 and 3. The same thing. I have another 1.1% of homes within this interval with energy consumption between 3 and 5. So these numbers means the percentage of a home with energy consumption for this particular class. For example, for this one, 0.233, that will be 23.3%. So that means I have 23.3% of homes with energy consumption between 7 and 9. Okay, so you understand this is my frequency table and this is my tabular format to show the frequency of observations in a specific interval. Okay, that's the tabular form. And then let's take a look what kind of a graphic format we have to show this frequency distribution. One thing I wanted to show you is I will show you how to draw a histogram by hand. Okay. Let me go back. Let me go to my next slide. Let me find my pen. Okay. Now this is my frequency distribution table. I have my frequency and a relative frequency here. So you understand this table perfectly, I assume. So now let's take a look at my XY coordinates I have here. So for the first class, I have 1 home with energy consumption 1 to 3. So what I'm going to do is so you look at my x-axis. I can find my first class, which is between 1 and 3. And how many home I have? Yes, 1 home. So probably 1 is here. What I'm going to do is I'm going to draw a rectangle, or I would say I'm going to draw a bar. Okay, a rectangle bar. So again, I'm doing the second group. Energy consumption between 1 and between 3 and 5. Here, go to my coordinates here. I have 3 and 5. Between 3 and 5, energy the number of a home I have is 1. So the height of my bar will be the same as the first one. Okay, so what about the third one? I have 11 homes. 11 is about here, right? So I'm sorry. Okay. I'm going to draw another rectangle or another bar. So as I have shown, you can see when I drew these bars, the height of the bar represents the number of homes I have. So you would do this next one. You have 21 will be here. I can draw. Okay, and then when you finish your histogram, you should have something look like the one I have on the right hand side. So this one here is a finished histogram. So let's take a look. So the height of the bar, like I said, represents the number of homes you have. And do you still remember that when we talk about relative frequency, you know these numbers here represent the percentage of homes fall within each of these classes. For example, I have bar A, bar B, C, D, and E. So A is the third class, so it has 12.2% homes within this interval. And for B bar here, we have 23.3%. And for C, we have 27.8%. When for D, 18.9%. And E, we have 10%. So you should understand, because we said, as you look at these different bars, and then I hope you can understand, it's fair for me to say the size or the area of the bar kind of represents the percentage of homes within this interval. So for example, for this one, the area of this bar C kind of represents the percentage of homes I have with energy consumption between 9 and 11. Okay? Again, I will repeat. It's fair for me to say the size or the area of the bar represents the percentage of homes I have within this particular interval. Okay, so again, let me go back to remember the frequency distribution definition we talked about earlier. It says either in a tabular, we've already talked about the tabular format, which is our frequency distribution table here. And also it says or a graphical format. So histogram is a graphical format that shows you the distribution, the frequency distribution of energy consumption here. So if you look, it's more like a visual representation. So you will, by looking at your histogram, you can know where is the most, or where is the which one is the class with most homes. It's very obvious. The class with most homes will be the interval C, between 9 and 11, and a few fewer than this will be B, with energy consumption between 7 and 9. So this is kind of like a visual representation of the frequency distribution. So you can look at your histogram, you will know how the frequency, energy consumption frequency is distributed. Okay, so this is a histogram. One more thing I wanted to talk about histogram is I'm going to about the class interval. Remember, I decided on 9 classes, and with each class has the same interval. So if you want to draw a histogram of your own for some kind of data you have to decide how many classes you need, and then what is the interval for these classes. So I wanted to talk a little bit more about the class interval. And there's a few things you need to pay attention to. So when you decide on your class intervals, you have to make sure that your class intervals are equal in width. For mine, my class intervals are the same. All of them are 2, right? You can remember I have energy consumption between 1 and 3, energy consumption between 3 and 5, and then the intervals are equal in width. And then the class intervals are mutually exclusive. This means there's no overlaps among your classes. You cannot say, okay, the first class is between interval from 1 to 3. The second interval will be between 2 and 4. So there will be, if you do things like this, there will be an interval between your classes, and then that will be hard for you to decide which home be put in which intervals or which classes. The third thing you need to be careful will be your class interval should cover all points in all data set. Remember, I have 90 homes, and then my 9 classes cover all 90 homes. So that's something you also need to be very careful about when you decide on your class intervals. And then one more thing I want to talk about my frequency table is, remember I've already showed you how did I calculate the relative frequency. And then one more thing I want to show you is called cumulative frequency. So what is cumulative frequency? I'm going to show you this. Look at these numbers. For example, the second one, if you look carefully, you will find this number will be this number added up with this number. This number will be these 3 numbers together. This number will be these 4 numbers together. So I will give you a definition of cumulative frequency. Cumulative frequency will be all frequencies so far. So far means, for example here, so far means so far to energy consumption of 5. How many homes so far I had? So what you're going to do is you're going to add these 2 relative frequencies together. One more example. All frequencies so far for this one will be all frequencies so far to the point of energy consumption of 7. So up to energy consumption of 7, how many homes I have? What you're going to do is you are going to add these 3 numbers together, and then you're going to get 0.144. So let's take a look how we are going to interpret these cumulative frequencies. So for example, this one, if I convert this one into a percentage, will be 14.4%. So for this number, that means I have 14.4 homes with energy consumption equal or less than 7. That means cover all homes with energy consumption from 1 to 7. Okay, so that means that is what meant by cumulative frequency. Okay, let's take a look at the relationship between histogram and smooth curve, or sometimes in mathematics we call density curve. So first of all, look at the histogram, which will be the shaded bars here. So you understand each of these bars here kind of represent a percentage of homes, or using a general term, if we are not talking about energy consumption example we talked earlier, we are talking about in general. Or we'll say, okay, each of these area, the area of each of the bars I have here, each of these area represents a percentage of scores or data points within this particular interval. You understand this because we talked about this earlier. And then, so if you look at all these shaded bars, if you add all of them together, it will be 100%, right? Because it represents the total number of data points you have. Okay? And then in mathematics, Sometimes we can find a density curve. Density curve is a smooth curve. Look at the smooth curve I found here for this particular histogram. And you will say, can I randomly draw a smooth curve to match my histogram? The answer is, of course, no. Because when you find the appropriate smooth curve, you have to make sure. See, look, this is my smooth curve. You have to make sure the area underneath the curve, remember, underneath the curve, here's my curve. The area underneath my curve will be all this area underneath the curve. When you find the appropriate smooth curve, you have to make sure the smooth curve, the area underneath the smooth curve is the same as the area of all your bars. Why is this important? You know it because the total area of your bars represents 100% of your data points. And then you have to make sure the smooth curve or the density curve you find for your histogram also have the same area underneath the curve. Okay? Let's take a look at a special kind of a histogram. So I would like you to take a look at the histogram I shaded in red. So if you take a look at it, you might have already noticed this histogram is symmetrical. Here is the central line. Did you see the central line here? Imagine if you fold your histogram along this line, you should see, or you should imagine that if you fold your histogram along this line, your histogram will overlap perfectly. Means what, the left hand side and right hand side, it will be the same. They can overlap perfectly. Another thing about this histogram is where you can find the largest bars, the biggest bars. Your answer will be you can find the largest bars in the middle. See, the area of these two bars are the biggest. And then while your value of your data point decrease towards the lower end, the size of the bars decreases. It's the same thing on the right hand side. With the value of your data point, increases towards the higher end, the size, did you see that? The size of your bars also decreases towards the lower end, decreases towards the higher end. It's telling you most of your data points are in the center, and with fewer data points on the right hand side as the value increases. Fewer and fewer data points with your with the value decreases towards the lower end. Okay, so here is the characteristics again. More data points in the center, fewer data points towards both ends, right? So if you have a histogram like this, we call this histogram is normally distributed. Normally, so you will know, I can also find a corresponding normal curve for my normal distributed histogram. So here is my normal curve. So normal curve, because if you understand those characteristics of this particular histogram, you should know the characteristics of this normal curve. It's the same. So if I ask you, what are the characteristics of this normal curve? Your answer will be, see, did you see the area underneath the curve? Where you can find most data points? Here, in the center. See, in the center you will have more data points. And with the value increases towards the higher end, you can find, did you see, the area underneath the curve actually decreases. It's the same thing on the left-hand side. With the value decreases towards the lower end, you can see the area underneath the curve also decreases. That means on both sides, towards the ends, you have fewer data points. Okay? So you get an idea how we convert normal distributed histogram into a normal curve. And then let's focus more on the normal curve. So the normal curve have several characteristics, and then on this slide I want to be specific. First important characteristic of a normal curve is mean, median, mode are the same. And you will ask me, where is the mean and the median mode? It's right here in the center, okay? Because it's symmetrical, and the mean, median, mode will be in the center of your normal curve. It's right here, okay? So another characteristic is normal distribution or normal curve is symmetrical. So that means if you fold your normal curve or your normal distribution, sometimes we call normal distribution, sometimes we call normal curve, they're the same, okay? So if you fold your normal curve or normal distribution along this central line, you will find it's perfectly symmetrical. That means 50% on the left-hand side, 50% on the right-hand side. When I say 50%, you understand what I'm saying, right? I'm talking about 50% of the area. And then 50% of the area means 50% of data points on the left-hand side, another 50% of data points on the right-hand side. You might have this question, or you might not, but I just want to talk about it. And then you might have this question, say, why bother to turn a histogram or into a normal curve, or to try to find a normal curve for my histogram? The reason is very obvious, because if you look at your histogram, you have those intervals, right? If we go back to our example about energy consumption for the 90 homes, you understand, so we have like the first interval will be from 1 to 3, the second one will be 3 to 5. So you can, for using an histogram, you can represent the percentage of homes within this particular interval. But your intervals here have already been predetermined by you. You only have 9, for that example, you only have 9 intervals or 9 classes. So that means what? Your intervals are not continuous. It's not very possible for you to randomly find an interval and ask, say, tell me how many, what's the percentage of homes within this interval. For example, maybe, let me get my pen again. Let's take a look. For example, you want to find this interval. Instead of doing the interview you have already decided, you decided about this interval. And this interval will cover, in your histogram, will cover this area and this area, right? And then you will say, okay, tell me what is the percentage of homes within this interval. It's hard for you to calculate, because your interval is not determined like this interview you want to calculate on. So, but if you take a look at a smooth curve becomes like continuous. you can mathematically, it will allow us to calculate any interval within underneath the curve. For example, if you want to calculate this interval from here to here, okay, I'm sorry, it's hard for me to control the pen with my computer, okay. You want to look at this interval from here to here. Mathematically, we will be able to calculate for you. And then if you want to from this interval to this interval, okay, that will be from here, from this line, okay. And then you will ask, okay, what's the percentage of homes within this particular interval? I will be able to calculate the area of this interval and to tell you the percentage of a home within this particular interval. So again, by using smooth curve, it will make it possible for you to calculate any percentage within any interval you want to work on. Okay, so this is a good thing about smooth curve as compared to histogram. Okay, now this is the characteristics about a normal curve or normal distribution. And then once again, one most important characteristics of the normal distribution is not only mean, median, mode are the same, symmetrical. Remember, where for a normal curve or a normal distribution, where you can find the most data points? The answer is obvious because the area is the biggest in the center here, right? So your answer will be, one more characteristic of a normal distribution will be you can find the most data points in the center, okay? I wanted to give you a good example of good examples of normal distribution will be people's heights or people's blood pressure. And then why you can now you should be able to understand why we say people's heights or people's blood pressure will be normally distributed. Okay, here's in the center, here's the mean, right? Here's the mean. And then you understand most people will have heights close to the mean. So that means what? Along the mean here, you can find most people. Okay? But with the height increases towards the higher end, you can find fewer and fewer people. So otherwise, you will have, if it's not the case, probably you will find, okay, most people will be like 6 feet or 6'2" tall. Okay, but that's not the case. Most people will be found with the average height in the middle. And with the height increases towards the higher end, we have fewer and fewer people. With height decreases towards the end, we have fewer and fewer people. Okay? The same thing will this will be the same thing for blood pressure. Most people will have normal blood pressure close to the mean. With blood pressure increases towards the higher end, we have fewer people. With blood pressure decreases towards the lower end, we have fewer people. So that's normal distribution. Okay. Now, one more thing. Sometimes I've said sometimes we say this is normal curve, or sometimes we just say it's normal distribution, and then sometimes we even say we call this bell curve, because if you compare the shape of a normal curve, it's pretty much like a bell like this. So sometimes we say bell curve. You should understand. You should know if someone says a bell curve or normal distribution, that person is talking about the same thing. Okay. Okay, let's take a look. I have 3 distributions the one in the middle, and then one on the right hand side, and one at left hand side. So if you look at the one in the middle, this one in the middle is the normal distribution. Normal distribution is what? You still remember one of the characteristic for normal distribution is it's symmetrical. So if you look at the one in the middle, it's symmetrical. This one is the normal distribution. It is symmetrical means it's not skewed. So it's skewed means it's if a distribution is skewed like this one and this one, it means what? It's not symmetrical. Mathematically or in statistics, we have a formula can use to calculate skewness. If you look at the formula for the skewness, remember we talked about the normal distribution. One characteristic is the mean and the median are the same here in the middle, right? And then if you look at the formula, X bar is the mean, uppercase M means median. So mean and median are the same for normal distribution. So skewness value for normal distribution will be 0. So 0 means there's no skewness. That means what is symmetrical. So you understand skewness is a measure to tell you whether a distribution is normal distributed or it's not. If the skewness does not equals to 0, that means what? That distribution is skewed. If a distribution is with a skewness of 0 means that that distribution is normally distributed. It's symmetrical. Okay. So look at this one. So this distribution we say is negatively skewed. The reason for that is for this particular distribution, you should be able to see we have larger area underneath the curve on the higher end. I mean higher end because this is my x-axis. The value increases towards this hand. This is my x-axis. Okay, so you understand for this one, we have larger area underneath the curve towards the higher end. That means you have more data points on this end. If you look at the formula, that means because you have more data points here, higher values. So your x bar will be smaller than your median. Okay, because you have more data points here. The median is the midpoint of your data points. Since you have more data points here, so your midpoint, the median will be more towards this end. So that means your mean will be smaller than your median, and then you are going to get a negative skewness value. This will be the opposite for this distribution. You have more data points because the area underneath the curve will be larger towards the lower end. That means you have more data points on the lower end. So since you have more data points with lower values, that means your median, the midpoint of your data set, will be pulled more towards this end. And then that means you will have your x bar will be larger than your median, and then you are going to have a positive skewness. And so this is why we call this distribution positively skewed. Okay, again, positively skewed means you have data points towards the lower end, and then it is not symmetrical, it's skewed. For negatively skewed distribution, that means you have more data points towards the higher end, and it's not symmetrical, it's skewed. Okay, so that's how skewed distributions is compared to normal distribution. Okay, now let's come to our final thing about z-scores and the probabilities. Before we talk about z-scores, I want you to first of all look at a question I would like you to answer. So my question is like this. In a standardized test, the mean and standard deviation of students' test scores are the mean is 75 sigma, sigma, which means the population standard deviation is 15. So if you're talking about the whole population, mu, I use mu, which is a parameter. I use mu means a population mean. The mean is 75. Sigma is population standard deviation, which is 15. So, or if you're talking about example, I will use x bar and lowercase s to represent example mean 75 or example standard deviation 15. But anyway, there's a standardized test, and then the student test scores have been calculated, and then the mean is 75, the standard deviation is 15. And I have a question for you. Your test scores in this test is 90. What is the percentage of students whose test scores are higher than yours? Are you able to answer this question for me? After we have been talking about the smooth curve, and then we have been talking about the areas underneath the curve. When you read this question, did this question ring a bell? Okay, let's take a look at my next slide. Okay. So I give you a kind of like three pairs of graphs here. What I want to show you is if you first of all look at the red shaded histogram, you understand, because this is normally distributed histogram. In the center will be the mean or the mu, population mean. If I have a data point A here, and then you understand by using a histogram, so the area for these 4 bars here, bar 1, bar 2, bar 3, bar 4, the total area of these 4 bars will represent what? Will represent the percentage of data points smaller than A, right? And then what about this? What about this one? I have a data point B here, and then you understand perfectly if the area to the right hand side of B, the area of these 2 bars represents the percentage of scores or the percentage of data points larger than B, because it's to the right hand side of B, right? This is what something we talked about, and you should understand it based on our discussion about the bars, about the bars in the histogram. Okay, so what about the bars to the left hand side? This bar, all these bars to the left hand side of B. If you add the area of these bars, all these bars together, you will be able to find the percentage of scores or the percentage of data points smaller than B. Okay, it will be the same thing, but I have A here, I have B here. Look at those bars in between A and B. This bar, this bar, this bar, this bar, this bar, this bar. If you are able to add all these areas of these bars together, you will be able to find the percentage of scores larger than A but smaller than B. We are talking. If you understand this with histogram, you should be able to understand the same thing about normal curve. So I have A here, I have B here, I have A here, B here. Okay, this shaded area underneath the normal curve represent the same thing as we talked earlier about the bars here. This shaded area underneath the curve represents what? Yes, it represents the percentage of homes. If we are talking about the energy consumption example, or generally speaking, the shaded area represents the percentage of data points smaller than A. Remember, this is the lower end. What about this shaded area? It's the same thing. B will be value, or will be a data point here. And then the shaded area represents the percentage of data points that are smaller than B because it's towards the lower end. What about the shaded areas here? If you know area B here, the total area B, you know area A here, and then will you be able to find this area? It's easy. If you know this area, and you use this area, subtract this area, you will be able to find this area. And then if we want to interpret this area, you know this area represents the percentage of scores larger than A but smaller than B. Okay? And then the question is, you told me, I told you, okay, this area represents the percentage of scores lower than A. This area represents the percentage of scores lower than B. This area represents the percentage of scores larger than A, smaller than B. And then the question is, how can we calculate these areas to find out these percentages we want to know? Okay, so in my next PowerPoint slide, I give you this is in summary. So now I believe that you understand perfectly what does each of these shaded area represents. Okay, I want to what I show you here is called cumulative distribution function. Please don't freak out. I'm not going to ask you to do any calculation related to this complicated distribution function. I want to show you this function. The reason for that is I want to show you mathematically we have this function will allow us to calculate corresponding area underneath the curve. Okay, you don't need to calculate it, but I will show you a much easier way for you to calculate without using this CDF. It's cumulative distribution function. Okay. So again, you know this area represents a percentage of scores lower than A, percentage of scores lower than B. Oh, my B has been removed to here, but you know my B should be here. Okay, and then this percentage, this area represents the percentage of scores between A and B. Okay. Now, also as a summary, you understand the total area underneath the curve, like the total area of the bars in your histogram, represents the all total data points you have. That means that is 100%. So you understand the total area underneath the curve will be 100%, will be equals to 1. Okay, let's go back to my question. So your test score is 90. And what is the percentage of scores who scored higher than you in the test? And my answer is 15.87%. And we can go further, like your test score in this test is 90, and student B scored 45 in this test. What is the percentage of students who scored between you and student B? Okay. My answer is the percentage is 81.85. Okay, you will ask me, how did I get these numbers? I'm going to show you how. Your score is 90. Remember, 75 is the mean, 15 is the standard deviation. If you break down your score to mean and to standard deviation, you will find out, okay, your score 90 is the mean plus 15, which is the standard deviation. So you understand if I say your score 90 is 1 standard deviation larger than the mean. See, 75 mean, 15 standard deviation. So it's fair for me to say your score 90 is 1 standard deviation larger than the mean. 15 is 1 standard deviation, right? So your score is 90. That will be one standard deviation, which is 15 larger than the mean. 15 points larger than the mean, 75. You understand this, okay? And then the student B score, that will be 45. That will be 75, the mean, minus 15, one standard deviation, minus another 15. So that will be 75 minus 2 standard deviations. So it's fair for me to say student B has a score of 2 standard deviations smaller than the mean. 2 standard deviations smaller than the mean. If I represent this using formula, will be mu minus 2 standard deviations. For yours, will be mu plus 1 standard deviations. Okay? If you look at what I have here, I actually, it's not me, mathematicians actually find a way and did the calculations for us. Okay, if you look at here, because this is a normal distribution, in the middle will be our mean, right? And when you look at this one, this point will be 1 standard deviation above the mean. Here will be 2 standard deviations above the mean. Here will be 3 standard deviations above the mean. It's the same thing. If you understand what we have on the right hand side, you should be able to understand what we have on the left hand side. For this point, it will be the mean minus 1 standard deviation, and I can say this point is 1 standard deviation lower than the mean, or 1 standard deviation below the mean. Below means what? Is towards the lower end. This point is 2 standard deviations smaller than the mean, or 2 standard deviations below the mean. This point, 3 standard deviations smaller than the mean, or 3 standard deviations below the mean. You understand this perfectly, okay? And then one good thing of have these points here, the mean, 1 standard deviation above, 2 standard deviations above, 3 standard deviations above, 1 standard deviations below, 2 standard deviations below, 3 standard deviations below. We can cut the area underneath the curve into different sections or into different parts. For this particular part, we already, by doing calculations, we already know the area underneath the curve between the mean and 1 standard deviation above the mean. There are 34.13% of data points between the mean and 1 standard deviation above the mean. What about this one? This one is between 1 standard deviation above the mean and 2 standard deviations above the mean, we have 13.59%. And the same thing, you understand this, between 2 standard deviations above the mean and 3 standard deviations above the mean, we have 2.50%. For this one will be, if you look at this area, you know, because this area is towards the right hand side, means towards the higher end, that means 0.13% of data points is larger than the mu plus 3 standard deviations above the mean. So the same thing on the left hand side, okay? 34.13 for this area between 1 standard deviation below the mean and the mean, and 13.59% between 1 standard deviation below the mean and 2 standard deviations below the mean. 2.15%, because it's symmetrical, so you will see these numbers, these percentages are the same because it's symmetrical. Okay, now go back to my question. Your test score is 90. What is the percentage of students who scored higher than you? So tell me, where is the area shows that higher than you. Let me go to my, I'm sorry. Okay, so look at the, my question is, the percentage of students scored higher than you. What are the areas represents the percentage of students higher than you? It's easy to understand. This area, and this area altogether represents the percentage of students scored higher than you, right? Because these three areas are towards the higher end. Your data point is here. So this percentage together with this percentage and together with this percentage altogether represent the percent of students scored higher than you. If you add these three percentages all together, and you will be able to see the answer for this question will be 15.87, because the total area underneath the curve is 100. You can use 100 minus 15.87%. You can get 84.13%. And then where is the 84.13%? That will be towards the lower end. And your interpretation of this will be, if you add all these percentages together, and then you can get the percentage of scores scored lower than you, and your score is 90. That means what? These areas to the left hand side of your score means the percentage of students scored lower than 90. Okay? My second question is, there's a student B. You understand, student B score 45 is 2 standard deviations below the mean, which is here. Your scores, let me get my pen, okay? The student B score is here. Your score is here. I'm asking you, what is the percentage of scores? I'm sorry. What is the percentage of students scored between 45 and 90? Scored lower than you but higher than student B. You, based on our discussion, you should know the percentage between you and the percentage of students scored between you and student B will be this area, and this area. And you know this area is 13.59, this area is 34.13%, this one is 34.13%. You add them up, and then your answer will be 91.85% between you and student B. Okay? Are you quite happy about calculating knowing someone's score and be able to calculate a specific percentage I asked you to calculate? Try to understand this concept, and then I may ask you to do some calculations in the practice exercises and some quiz. Okay, so let me go back to the question I showed you earlier. And in that question, I asked you, your score is 90. Okay, so 90 is your raw score. Student B got 45, and I've already showed you is the mean minus 2 standard deviations. So I can express your score like 1 standard deviation above the mean. And student B's score will be 2 standard deviations below the mean. Your score from the test is 90. And then the student B score in this test is 45. 90 and 45 are the raw scores. Raw scores are the data you collected from your sample or collected from your participants. Score do not necessarily has to be test scores. For example, if you collect data, if you collect blood pressure on your participants. And then the value for that for your participants' blood pressure, I can still say raw score. So raw score is the number you collected directly from your sample. Okay. But what about z-scores? So 90 is your raw score, 45 is the raw score for student B. But I also express the two raw scores in terms of standard deviation and mean. So I said, okay, your score is 1 standard deviation above the mean. Student B score is 2 standard deviations below the mean. Okay, I'm expressing your raw scores in terms of standard deviation and mean. What I'm talking about is the z-scores. So your score is 90 minus 75 divided by the standard deviation is 1. That is 1, the number is positive. So this is why I say your score is 1 standard deviation above the mean, because it's larger than the mean. So it's 1 standard deviation above the mean. Student B is 45 minus 75 divided by 15 would be a negative 2. So the number is negative. That means the student B's test score is below the mean. How many standard deviations below the mean? 2 standard deviations below the mean. If 90, 45 are the raw scores, here 1 and negative 2 are the raw scores. Okay? I'm sorry, 1 and negative 2 are the z-scores. So you will ask me, what is z-score? Z-score is a kind of a standard scores. Okay? Let me first tell you, I'll give you a definition about standard scores. Standard scores are standardized in units of standard deviation to represent how close a raw score is to the mean. How close a raw score is to the mean. Okay? Based on the previous example, you should know how close to the mean. For example, you got 90. I will tell you, okay, how close is your score to the mean? I express your 90 points in terms of the mean and standard deviation. I said, okay, your score is 1 standard deviation above the mean. So you know the relationship of your raw score with the mean. Okay. So to be exact, z-score is a type of standard score, and it indicates how many standard deviations a raw score is away from the mean. Okay, so this is the formula for calculating z-score. X here is your raw score. You're going to use your raw score minus mu, which is the mean, divided by standard deviation. Okay, and then you might ask me why we wanted to convert our raw scores to z-scores, and then I've already shown you why. Because by turning your raw scores into z-score, you can use this, right? And then you will be able to calculate the percentages you want to know. For example, again, the same question. We have student A, test score 105, student B 45, student C 100, student D score 50. And then my question is, what is the percentage of students who scored higher than A? Student A got raw score 105. I'm going to turn or convert the raw score into z-score. I'm going to use 105 minus using the I'm using actually the z-score formula. Okay, for calculating z-score, I plug in the raw score 105. I plug in the mean 75 divided by 15, which is the standard deviation. I got 2. So that means what? Student A has a test score 2 standard deviations above the mean, and you will be able to see it's right here. Okay, so I'm asking you the percentage of students who scored higher than A, which will be here. Okay, will be this area will be this area, add this area. So if you add these two percentages, you will find the answer will be 2.28%. Okay? Now, again, back to the question, say why we want to convert raw score into z-scores. The reason for that, with a z-score, you will be able to calculate the percentages like shown in this example. Okay? Let's do one more practice. You have student A and B. Student A scored 105. Student B scored 45. And then let's convert these two raw scores here. 105 and 45. These are the two raw scores. Let's convert into a z-score. So it's easy to calculate. You plug in a number, you will be able to find out student A is 2 standard deviations above the mean. Student B is 2 standard deviations below the mean because it's negative. So here is student B. Here is student A. And then I'm asking you the percentage of students who scored between student A and B. Okay? And then you understand you needed to add these 4 areas. This area, this area, this area, this area all together. And then if you add them up, you are going to find 95.44%. In other words, there are 95.44% of students scored lower than student A, but higher than student B. Okay? Let me go to my next slide. Okay, one more question. I have another student, student C. Student C scored a 100 on this test. Okay, I'm asking you, what is the percentage of students who scored higher than student C? Let's, of course, the first thing we need to do is we convert this raw score 100 into a z-score. You plug in the number into the formula. 100 minus 75 divided by 15 will be 1.67. Okay? Oh my goodness! This time you might have a problem, because when you look at the graph we used for our previous questions, you will see 1 standard deviation, 2 standard deviations, 3 standard. These numbers are all integers. These are not. So if you look at my graph here, 1.67 probably should be between 1 standard deviation above the mean and 2 standard deviation above the mean. Probably it might be somewhere here. Okay. So you will know if I ask you to calculate the percentage of student higher than student. This is student C. Okay. And then I ask you to calculate the percentage. It will be this area towards the higher end. But the problem is, how can you calculate this? Because this number you cannot find in this graph. So with this type of question, with the z-score which is not integers like this one, you have to use the table in your textbook. And then you can find your textbook, you can find the table in your textbook in here. You can find in Appendix B. And then the Appendix B in your textbook is the selected values from a normal curve table. And then you can find the z-score there. If you go to Appendix B in your textbook, you will be able to find, okay, in your textbook, the table on that page gives you 3 columns. One is the z-score. One is the area between the mean and the z. The z-score, the area between mean and z will be here, area B. And then the table also gives you the area beyond z. Z is here. Beyond means to the right hand side. So your table in the textbook tells you the percentage represents area B, and the percentage represents area C. So you have this number 1.67. If you go to your table in your textbook, you can find the number 1.65. And this is pretty close. If you look at the corresponding area beyond Z, which is C, the table tells you is 0.0495. It's pretty small, but you can do some rounding and you will find area based on the table in your textbook is 5%. Okay? So this is how you are going to use the table. So if I ask you to calculate the percentage of students who scored lower than student C, you will be able to lower than student C will be the area to the left-hand side of this Z. So if this is 5%, this total area, red shaded area here, will be 95%. Okay? So because you understand the total area underneath the curve is 100%. Let's do one more question. So student D scored 50. If I'm going to convert this student raw score into a Z-score, that will be 50 minus 75 divided by 15, that will be negative. This number is negative. Negative means what? Negative means what? The Z-score will be below the mean, or to the left-hand side of the mean. Let's say it's right here, okay? Here is student D, okay? And then my question is, what is the percentage of student who scored lower than D? If you go back to the table in your textbook, you will find, okay, all these Z-scores listed are positive. There's no negative Z-scores. But you need to understand, because one of the characteristics for normal distribution is what? It's symmetrical, okay? If this area here, you know, this point here is positive 1.67, and then this point here is negative 1.67. And you should understand this area C will be the same as this area on the left-hand side. If this area is 5%, this area will be the same 5%. Okay? Now let's before I finish up, I want to do a little bit summary. Okay? Let me go back to my previous slide, and then we have already looked up the number 1.65. Find this area is 5%, and then 5% is fair to say 5% is not big. It's not a big percentage. So I hope you can understand if I say, okay, because here is 5%, I will say for this particular test, it's very unlikely to find a student whose test scores is 45. I'm sorry, because this student actually scored 100, okay? Because this is here is 100 or 1.67. So and 5% is a small percentage. And then if I say, okay, in this particular test, it's unlikely to find a student who score 100 or higher, right? 100 is here. Higher is this area, because this area is small, so it's kind of fair for me to say in this particular test is very unlikely. If I'm not saying very, if I can just say it's unlikely to find a student scored 100 or higher, because this percent is small. Okay. The reason I'm talking about this, because this is related to a next topic we are going to talk about. So I want to get this, and then you will maybe feel easier for you to understand what I'm going to cover in next chapter. Okay, thank you. That's all I want to talk about.